Okay, so today we're going to wrap up this module on oxidation state 1 with the chemistry of the amines. We're going to finish that off. And then your exam will open today at 2:15. It will close tomorrow at 2:15, so remember to review and submit. And then sometime tomorrow afternoon I'll post your scores, and then Friday I'll spend some time calculating your interim grades and uploading those into SOAR. So you have those for your advisement. It's coming up. So we had left off talking about the presence of nitrogen atoms in natural products, which are called alkaloids. And there's a lot of different alkaloid classes. And usually they're going to have some sort of common skeleton. So for example, the tropane, you can see that in cocaine, the natural product there. Some other natural products, well, maybe one, is morphine. And so to the left here, that's the morphine skeleton. It's typically drawn that way when you see it in the literature, but again, it's polycyclic, so it has a three-dimensional shape to it. And then here's a tertiary nitrogen embedded in a six-membered ring. So what's interesting about morphine, again, it's a natural product that's synthesized in the poppy plant, which is, I guess, this pod here, like green pods. I've never seen one in real life. I think they're about the size of a tennis ball or something. But basically, the pod produces this latex. So like if you cut it with a razor blade, this like Elmer's glue looking stuff comes out. And then from that, morphine can be isolated. So its therapeutic indication is it's an analgesic, so that means it's a painkiller. And so if you've ever been, to the hospital, whether it's an emergency or some planned visit, you ever see that pain scale with the emoji faces? Are you happy or are you like really in pain? That was actually developed by Purdue Pharma for the reason of selling OxyContin. So if morphine is sort of the benchmark for alleviating pain, if we say it's a benchmark of 1, chemists want to improve upon things. So if you look at the difference between OxyContin and morphine, this phenol has been turned into an ether. So that's something that we talked about. This hydrogen has been oxidized, so that carbon is now a tertiary alcohol. So that carbon's up 1 oxidation state. This secondary alcohol has been oxidized now to a ketone, and then that double bond has been reduced. So the skeleton is still there, but with a couple functional group modifications. There's this synthetic analgesic OxyContin, and one of the driving forces for any business is to make money. So OxyContin pushed really hard to have doctors prescribe this. There's I think it's a series on Hulu called Dope Sick with Michael Keaton, who is the best Batman there ever was. He's a doctor, and he talks about, interacting with the sales rep that are getting him to push this and how it affects small communities and the socioeconomic impacts of that with the individual and then health and crime and that sort of stuff. But there are other derivatives of this. So like heroin, these alcohols have been turned into esters. And so then you get a different sort of enhancement of the analgesic / euphoria effect. And this one, even though the writing's buried here, this is naloxone, otherwise sold as Narcan. And so this is, hopefully I remember this word, it's an antagonist. So it basically displaces this in the receptor, and it doesn't elicit that euphoria. So people that are overdosing on opioids, this is what's administered to kick this out and replace it with that, and sort of prevent an overdose. But in essence, the spice shall flow. So alkaloids, a lot of the chemistry in your textbooks have been, developed for the purpose of people wanting to make these alkaloids and make derivatives of them. And one of the first examples of this was the synthesis of tropinone. So notice here there's that ketone on the tropane skeleton. And this was done by Sir Robert Robinson, who won a Nobel Prize for these investigations. And, even though this looks, kind of complex in a way, the way that he did it was to break it down basically into methylamine, this 4-carbon dialdehyde, and then this diacid, which has a ketone in the central carbon. And so through just a series of oxidation state analysis, was able to take these three in a condensation to make basically those 2 rings. And then some chemistry we'll learn later, these acids are burned off or degraded. So this type of synthesis is called biomimetic. And what that means is you have something really complex and you want to make it in a way that nature makes it without anything terribly fancy going on. We'll talk about more of the specific reactions that are happening in this in later modules. But again, the goal of major pharmaceutical companies is to find some target molecule, whether it's from a natural source or a synthetic one, sort of maximize its potency and sell it for some therapeutic indication. So another important nitrogen-containing molecule is aniline, and we saw that a couple different times this semester. So during the conjugation and aromaticity, we basically were talking about substituted benzene. So this is the aminobenzene, and so that's called aniline. And the kind of origin of modern chemistry was people wanted to find dyes for clothes, and that was inspired by the colors of plants. And one of the first dyes people were interested in is this mauve or kind of royal purple. And so that's the color of mauvine. If you look at aniline, you can kind of see aniline monomers embedded in that structure. And so that highly conjugated system, when we talked about the difference between the highest occupied and lowest unoccupied molecular orbitals, the more pi bonds you have, that gap gets smaller, so the transition's easier and it gives rise to things that we can see. So color. And so the color that I use on these slides, you can make any color font you want in your presentations with these red, green, blue sliders. You don't have to just keep it to the normal Microsoft stuff. But color is a big sort of motivating psychological factor, I think, in our lives when we're at the store looking at things. What attracts your attention? It's typically color. And so as we talked about, that all arises from that UV vis spectroscopy. So another relevant thing about amines, in this case again aniline, this company BASF, if you've ever heard of that, it's a global company. This is what it stands for, so that's the German name, and you can see aniline in there. Soda is not your Coke or Pepsi. It's like hydroxide, sodium hydroxide or lye, stuff like that. So let's say So later founded. Look at how long that word is. But basically, this company was involved in Germany prior to World War II, and they were basically making the Zyklon B, which is hydrogen cyanide that was used in the gas chambers. And so what happened after World War II? Why were they allowed to exist? So they kind of dispersed, and then the global community said, well, you're making stuff that we need to live, and they allowed them to kind of recombine. So I think, overall, molecules from natural products or synthetic bulk molecules play a pretty important part in the comfort of our everyday lives. I think we live a lot longer because the yield from crops is now higher, so there's a greater food supply. And then if we do get sick, there are these medicines that help us not bitch and moan so much when we're sick, or even save our lives. So let's start looking at the different sort of functional groups that nitrogen can be a part of, and how that relates to hybridization. And now, because nitrogen has 3 bonds and 1 lone pair, how that lone pair can act as a base, and how the hybridization affects that. So again, our neutral bonding pattern and when I say 3 bonds, again, that can be an assortment of different types of bonds based on the functional group. So your typical amine, it's just 3 sigma bonds and a lone pair. Then we can go up to where the nitrogen's in a double bond, or it's in a triple bond, but it's still 3 bonds and a lone pair. So on the structure shown, these are nitrogen heterocycles, so a ring with nitrogen in the ring. When you look at the nitrogen atoms, you can count 3 bonds, and then the lone pairs are there. We want to figure out in what type of orbital does that lone pair exist? So here we have imidazole, caffeine, and nicotine. So why is imidazole on there? As we'll see later this semester, it's part of the side chain in the amino acid histidine. So imidazole has 2 nitrogens. So we can count the bonds, 1, 2, 3. So those are sigma bonds. Then here, this one we have sigma, sigma, and pi, so that's 3. Put those lone pairs in. For caffeine, now we have 4 nitrogens. Again, you can count the bonds. Just throw in the lone pairs, and then nicotine has 2, so there's the lone pairs. What is kind of deceptive about nitrogen, so imidazole, you see the 5-membered ring in the separation of the 2 nitrogens? You can kind of see that in caffeine as well. When we look at nicotine, that nitrogen has sigma, sigma, and sigma lone pair. That ring has no double bonds. So that nitrogen is sp3 hybridized. The nitrogen in the aromatic ring, so that's sp2, because we can see that nitrogen has a pi bond to carbon. The pi bond arises because there's a single electron in the nitrogen p orbital and a single electron in that carbon p orbital. So that means this lone pair resides in an sp2 hybrid orbital. So again, this nitrogen here, because there's no double bonds in there, it's easy to see that it is sp3, because you have sigma bond, sigma, and sigma. Now when you look at this one in imidazole, we see sigma, sigma, and sigma. So your first approximation might be to say that that nitrogen is also sp3, but it's not. This nitrogen is sp2 hybridized. The other nitrogen looks like the pyridine one because you have that pi bond. So this lone pair is also in an sp2 hybrid orbital. The difference between these two, the lone pair here, because you don't see the pi bond, is in a p orbital. That's part of the conjugated system. Does everyone follow that? So when we look at caffeine, this nitrogen here looks like the pyridine one. This nitrogen looks like the imidazole one. And then what about these? Because we see 1, 2, 3 sigma bonds, 1, 2, 3. These nitrogens are also sp2 hybridized. The reason that is, they're both next to a carbonyl. And so that lone pair of electrons can be delocalized through resonance onto the carbonyl. For that to happen, they have to be in a p orbital that lines up with the CO double bond. So the point of this is, if the electrons reside in a p orbital, they are not available to act as a base. So they either have to be in the sp3 hybrid orbital or in the sp2 hybrid orbital. So this kind of shows those two scenarios. I've simplified the imidazole to pyrrole, and then there's the pyridine, and then the red lobe. So that's your p orbital, and then this is your sp2 hybrid. In the pyrrole, those electrons are tied up in that conjugation, so they can't act as a base to abstract a proton. But in pyridine, they're kind of sticking out. They're waiting to form a bond, whether it's to a hydrogen or some other electrophile. So stated another way, these can undergo resonance, these cannot, because that orbital is 90 degrees from the pi cloud. So because nitrogen has that lone pair, they have basic reactivity. So by basic, I'm not talking about like beer versus champagne budget. I mean like the ability to abstract a hydrogen. So when you're able to classify the nitrogen hybridization, this is the trend. In sp3 hybrid, nitrogen is more basic than sp2 and more basic than sp. And so that relates to that percent S character. So this was 25%, 33%, 50%. Another way to think of it, there's so much of the p orbital that hybrid orbital is larger, and the lone pair extends out further from the nucleus. So when we talk about basicity, that's, again, the ability to abstract a proton from an acid. So throughout organic 1, we were talking about pKa, where that's the acidity constant. So for basicity, there is basicity constant, so pKb. But to normalize everything, we kind of invert the relationship and just call it a pKa. So what you'll notice in this reaction So the amine is protonated. So it is an acid, and water is the base. So water is abstracting a hydrogen from the protonated amine. That generates the amine plus hydronium. So the reason we do this is just to make things uniform to the Ka scale. And then just through our logical thinking, we just kind of invert that pKa to think about basicity. So that Ka was defined as the concentration of the amine times that of hydronium divided by the concentration of the protonated amine. And from organic 1, we can just take the logarithmic, the p function of each side. So p, again, is equal to the negative log. And the series of compounds that you see, that's the protonated amine. Remember, on the pKa scale, the smaller the number, the more acidic. So if we think about this in reverse, what hybridization is this nitrogen? So that's sp. So when it's protonated, it's negative 10 pKa. That means it's a really strong acid. So we can infer back from the neutral compound, for that to get protonated, it's generating a really strong acid. So that has to be a weak base. And then let's go to the other end here. What's the hybridization of that nitrogen? sp3. So this is 10.75. So it's a lot weaker. So it's a weaker acid, meaning that's a stronger base. And then the line there, these are all sp3, hybridized nitrogen. There was our sp, and so these are sp2. But again, the difference, the nuance between these two, from the pyridine, the lone pair is in the sp2 hybrid orbital, so it's available to bond. Then here it's not, because it's in the p orbital. So that's a stronger acid, which means that the starting compound perol is a weaker base. And since this is a weaker acid, the starting pyridine is a stronger base. So when we talk about basicity, really we're aligning it with this pKa scale. So sp3 is greater than sp2, which is greater than sp. And then the trend among sp3 hybridized nitrogens, when you classify them, tertiary is greater than secondary is greater than primary. Questions? So I'll go through these pretty quickly because we've talked about it. Again, both N atoms are sp2 hybridized. And then we want to figure out what type of orbital does the lone pair reside in. So for this Roman numeral 1 here, that was an sp2 hybrid orbital. And then here, that was the p orbital. So I think for that, choice B is correct. So which one is more basic? That would be the sp2. So again, that lone pair is tied up in conjugation. It can't donate to abstract a hydrogen. And so as a line on the pKa scale, that has a lower pKa value, which means it's a weaker base. So what is the hybridization? So that molecule by itself is called pyridine. So it's like a benzene that one of the CH groups has been substituted for nitrogen. The 5-membered ring, that was called pyrrolidine. And so just by looking at that, we can say that's sp3, and this one's sp2. And then from that series of compounds relating basicity to hybridization, the sp3 nitrogen is going to be more basic. I think that was the next question. So the pyrrolidine. The structure is okay. So I was teaching this class, I think, in this room 3 years ago in the fall. And so we were talking about these compounds, and a student mentioned Zin, which is basically a, like normally humans get nicotine through smoking, through tobacco leaves, but smoking is bad for you, causes cancer, that sort of thing. So these big tobacco companies have basically formulated nicotine as a salt in a pouch and delivers it another way. So you can see nicotine bitartrate dihydrate. So that means tartaric acid was used to form the salt, and then it has 2 molecules of water associated with that form of it. And then with that, there's these stabilizers and fillers and on all this other stuff to help keep it shelf stable. So my memory gave me one of these pouches. I took it back to the lab and dissolved it in deuterated chloroform to see if I could extract out the nicotine and see. Need to refer by NMR. And so this was the spectrum that was produced in the aromatic region. So let me. So when we look at this, the pyridine ring, there should be 1, 2, 3, 4 signals. And if we look at the numbers in red, that says 2, 1, and 1. This giant thing here, that's just from the solvent that it was dissolved in. But that does integrate to 4, and that's what we should see. These things here are just overlapping with one another. And so a colleague of mine had a pure sample of nicotine from Sigma Aldrich, and I ran that on the NMR and just stacked it with the thing from the Zin. So you can see these two. So now we have 1, 2, 3, 4 signals. Like they just overlap because of the other stuff in there is causing them to kind of coalesce. So we have 2, then the 1, and then the 1. So here's something to think about for a minute or two. So we have hydrogen 1, 2, 3, and 4. So based on the signal you see in the splitting or the coupling, so here's the numbers for the chemical shift. When you look at each one of those, what sort of splitting would you expect? And then where do you see it here that would line up with the correct response? Anyone have a? You said C. I guess I see an issue with that. Let me just point something out. So there's 4 total, right? If you look at that nitrogen as sort of where you're starting, you see 1 and 4 are like right next door. So on the spectrum, they should have similar chemical shifts, right? And so down here you see 2 signals that would have similar chemical shifts. So you can make a rough assignment. And then when you look at these and you consider like the multiplicity, you can kind of further resolve things. Yeah.
Is it B?
Yeah, I think it's B. So one way to figure that out, so we know 1 and 4 should be similar. Now, if we consider neighbors, H1 has like no direct neighbors, right? So in theory, that should be a singlet. H4 has H3, so that should be a doublet. Now, granted, between these, they don't exactly look like a nice singlet and doublet. You see at the top here, there's a little bit of extra splitting. What happens is that in these rings, even though like for H4, that's the direct neighbor for a doublet splitting, the smaller splitting is due to the fact that within the ring being constrained in these pi bonds, that 4 feels a little bit of the spins from 2. So you get the second little splittings there. And then H3, we were saying, so this H3 has 1, 2 neighbors, so you would expect that to be kind of a triplet. But again, these are not equivalent. And then there's this other long-term or long-range coupling. So that's how we could assign H3 to that. That looks the most complex because it has the most neighbors. And then the sort of through the ring coupling leads to all the other little stuff that you see. So again, nicotine is a natural product. It's produced in the tobacco leaf, and these large companies, the history of America, the evolution, a major crop was tobacco, right? And what do companies try to do? A tobacco leaf is not 100% nicotine, right? If you weighed it, then extracted out the nicotine, it'd be a very small percent. So chemists and biologists, botanists get involved. They're like, how can we alter the soil? How can we change the genetics to increase the percent? Say it was like, 1.5% nicotine. Even if you got it up to like 3%, you're doubling that yield now, and then you can make more money and blah, blah, blah. So the state of kind of organic chemistry now with these things is how can we alter the plant genetics? If you watch that show, that series, Dope Sick on Hulu, and you think about the amount of OxyContin that was being prescribed, they're making it, from a morphine derivative isolated from a plant. And think about the acreage size you would need to grow those plants and harvest that out. So like these big companies, they'll go to climates where it's favorable to do these things, alter the plant genetics so it increases the yield and allows them to produce more. So while we're on the topic here of nitrogen basicity, the prior discussion was about like just a neutral nitrogen atoms lone pair. What we're going to look at now is forming nitrogen bases that are much stronger. So to do that, we need to start with either a primary or a secondary amine, something that has an NH bond. So the pKa typically of that sort of functional group is about 40. So it's pretty weak acid when you compare it to an alcohol, which is like 16 to 18. So we have a pKa here of 40. If we want to turn that nitrogen into a really strong base, we can take an even stronger base. So butyllithium, that's one of those organometallics that we talked about that has a really strong carbon anion. And we can think of it as C minus Li plus. So that can abstract a hydrogen. Nitrogen already has a lone pair, so it gets a second one. So now we have this N- plus the counter ion, and this is called lithium diisopropyl amide. That name there is not the typical amide you're used to seeing, but in this context, amide means the nitrogen has a negative charge. And so now this is a really strong base. So we can use that to now in other acid-base reactions to abstract CH bonds. We won't get too much into that today for this module, but it's going to come back in another module when we start making carbon-carbon bonds. The other benefit of it is these isopropyl groups are pretty big. So even though nitrogen's negative charged, it doesn't act as a nucleophile. It just acts as a base. Again, meaning that it's just going to abstract acidic protons. It doesn't do nucleophilic additions. So now with the last, what do we got? What, 25 minutes. We're going to look at nitrogen as a nucleophile. And this is basically how do we get nitrogen into a molecule to make an amine. So the first couple reactions are going to be SN2 based. So nitrogen's the nucleophile. It's going to react typically with some alkyl halide. And remember that that SN2 trend. We want to make sure our electrophile is either primary or secondary based on how that mechanism happens. So the most primordial source of nitrogen is ammonia. But ammonia is not a good nucleophile for these, because what will happen is ammonia can react with an electrophile, and then what will happen is an acid-base reaction that will take ammonia to a primary amine that still has a lone pair. And so that lone pair can react again, then you'll get a secondary amine, then a tertiary, and then a quaternary. So ultimately, you'd end up with this messy product distribution of things where, say, you only wanted a primary amine. So to get around that, the three reagents that are shown on this slide are sources to introduce nitrogen into a molecule. So I'm going to draw a line here. The sodium azide and potassium thialimide have a nitrogen atom that is nucleophilic. The potassium cyanide, notice where the charge resides. The negative charge is on the carbon. So the carbon is the nucleophile, and it's dragging that nitrogen along. Now, the issue with all of these, it's not just N in whatever you want. The nitrogen's protected. So the reagent gets it in the molecule, and then you have to do another step to unravel it or reveal it to what you're trying to make. Sodium azide and potassium thialimide are easy reagents to handle. They're solids, they're pretty easy to weigh. Potassium cyanide, obviously, you got to take some more precautions with it. The acid of that HCN is what's really deadly, but because this is a solid, I mean, it's still toxic, but it's not going to like outright do you in by handling it. So when you install that nitrogen with sodium azide, look what you're bringing along, 2 other nitrogens that you don't want. Then with potassium thialimide, you have these carbonyl groups. So see this Li, so that says imide. An imide is a nitrogen that's like 2 amides. That's what the imide functional group is. And then potassium cyanide, you got to get rid of those triple bonds, so that carbon has to be reduced. But overall, what this is doing, it's preventing the nitrogen from reacting further, as is the case with ammonia. So here are the reagents: sodium azide, potassium thialimide, potassium cyanide. So those are your nucleophiles. And then this R1X is your electrophile. Again, since it's SN2, it's that bimolecular kinetics where you need a polar aprotic solvent and probably some heat to get the substitution to happen. So what do you end up with? An azide, a thialimide, or a nitrile? And so then you have to do something else to get it to an amine. So same thing for each case. And then the conditions for that deprotection vary. So I've lumped the sodium azide and potassium cyanide onto one slide to highlight the difference shown here. We're starting with a secondary bromide. So we have a good leaving group. Sodium azide, DMSO is our solvent, a little bit of heat. That installs the azide through substitution. But we don't want that, so we have to do a reduction, and we can use the hammer lithium aluminum hydride. All that's doing is expelling that N2 as nitrogen gas. And so now what we've ended up with is a primary amine. In the lower route, when we start with potassium cyanide, the carbon's the nucleophile. So it is getting attached to where that electrophile was. And since it's a triple bond to a heteroatom, it's at oxidation state 3. And so we can reduce that with hydrogen gas, an active form of nickel metal, and we still end up with a primary amine, but look at the difference between the top and the bottom. These two molecules are a series, and they're called homologs. So the primary amines here are basically separated by that CH2 group. That's called a homologous series. So kind of the take-home message is if you see CH2 and then NH2, if we think backwards, we can say that that part comes from cyanide and then a reduction. So the potassium thioimide gets its own slide. This is a named reaction called the Gabriel amine synthesis. So it's still SN2. We have a secondary bromide. We're using a polar aprotic solvent that displaces the bromide. And now this makes a thioimide. So that imide I'll highlight in blue. That's that bonding pattern to give an imide. So that has to be unmasked. To give the primary amine. And the reagent that does that is called hydrazine. So hydrazine and ethanol will unmask that. Does anyone know what else hydrazine is used for? So it's a fuel or propellant to launch rockets into space. In lab, you pour it. It has kind of a light yellowish brown color, but it looks kind of like dirty water, Hattiesburg water. So that deprotects that to give your amine. So again, all three of those reagents operate under the SN2 mechanism. And so, another way that you could make that is just use the DMS, the sodium azide to get the azide, then reduce that. You would end up with the same product. I think we have 3 more reactions to cover. 2 of them are similar, and then, we have 4. 2 sets of 2, basically. I kind of waffled last night about including these next 2 in here, but because we'll probably cover them again in the next module. The starting material for this amine synthesis is an amide. So more specifically, we can see the amide functional group. It has to be a primary amide, meaning that has to be NH2. So if we take a primary amide, treat it with bromine water under basic conditions, what happens is the nitrogen reacts with the bromine, and then this rearrangement occurs. So one thing I'll introduce now so we know what a carbonyl group is, and we're going to start talking more and more about this nomenclature. The carbon next to it is called the alpha carbon. And then if you keep going out, you just follow the Greek alphabet. So the carbonyl, our alpha carbon, this nitrogen gets bonded to that alpha carbon. Through a reaction of the amide nitrogen with the bromine, and then this rearrangement happens. What's nice about this reaction we're still making a primary amine, but look at this center here. So we couldn't do this reaction because that's a tertiary carbon. So when you look at, the amine classification and then what's bonded to it, you can sort of then pick and choose what is going to be the best reaction type to get there. So those first couple reactions we saw, we couldn't make that because that's a poor substrate for SN2. So the Hoffman rearrangement allows us to get to still a primary amine, but that carbon that's attached to the nitrogen is now branched. So an intermediate in that reaction is this structure that's shown. That collection of 3 atoms with that bonding pattern is called an isocyanate. And the question is, what is the hybridization of that carbon atom? Huh?
SP?
Yeah, so that's SP. You have a carbon with a sigma bond, then pi and pi. So again, you probably normally just used to seeing those in the alkynes or the nitriles that have a sigma bond, and then the 2 pi bonds are to the next atom. These pi bonds are on to different heteroatoms now. So way back, seems like a human epoch has passed since the beginning of the semester. Remember when we were talking about polyenes? So this is a type of polyene that's where the double bonds are next to each other, so it's cumulated. So we talked about cumulated, conjugated, and isolated. So that functional group has that cumulated diene system. Check something real quick. Okay. So it's sp hybridized, and then what is the oxidation state? It's going to be 4. So carbon, 1, 2 bonds to oxygen, 3, 4 to nitrogen. So 4 is the highest you can get, right? And we really haven't seen that too much. So these cumulated dienes can achieve that oxidation state. So that looks like CO2. So carbon dioxide, that's also sp hybridized with oxidation state 4. And unless you have a basement lab doing organic chemistry and trying to win the Nobel Prize, you can't take carbon up to oxidation state 5, right? So it can't be oxidized. It can only be reduced. And so what's special about that is it makes it more reactive now, right? Because it wants to go down in oxidation state. So these type of reagents we'll see again once or twice before the end of the semester about how they're used, specifically in the synthesis of peptides. We'll see an oxidation state 4 reagent that enables the synthesis of peptide bonds. So an analogous reaction to that is called the Curtius rearrangement. So the Hoffman rearrangement started with a primary amide. Curtius starts with this carbonyl azide. So that's called an acyl azide. So you still have that carbon bonded to a nitrogen, but now the conditions are a little different. There's no bromine. It's just you're heating it or applying a certain wavelength of light to initiate the rearrangement that gives you essentially the same product as a Hoffman would. So when you compare and contrast what's easier to make, a primary amide or an acyl azide, then do I want to work with bromine, or do I want to try things with heat or light? So those things come into play, practically speaking. So we have 2 more reactions. And so now all of that stuff was, how do we get nitrogen into the molecule? These next 2 are, what are the reactions of the nitrogen, and then how do we get it out of the molecule? So I believe this is a different Hoffman. I think there's just one F in this one. So this is an elimination, meaning that we're going to form an alkene. So we saw on the prior slide how to make this primary amine. And so this first reaction, this is what I meant by why we wouldn't use ammonia to install a nitrogen. So that nitrogen has a lone pair. If we treat it with an excess of electrophile, in this case methyl iodide, notice what we end up with. We've put 1, 2, 3 methyl groups. That's because we're starting with 2 hydrogens and a lone pair. So everything basically gets alkylated because nitrogen now has 4 bonds. It has a plus charge. The counter ion is iodine. And really what this is doing, it's making that carbon-nitrogen bond very weak. So we can treat with silver oxide in water. That's going to act as a base. And we're going to do an elimination from the alpha carbon with the most hydrogens. So this one has 3, the other one has 2, and that's your typical E2 mechanism. So it's really a matter of statistics when you're examining these. So the carbon with the most is going to win. And so wherever that nitrogen is and the carbon with the most hydrogens, that's where you're putting the double bond. So that's, in our classification, that's a monosubstituted alkene. So here's a slightly more complex example of that. Still have a primary amine, and it says what is the product. So, what'd you say? Yeah, it's going to be D. So A is the first intermediate because the methyl iodide is polyalkylating the nitrogen to make it a leaving group. So if we examine the carbons next door, there's 3 of them now. And then we say there's 3 hydrogens there, 2 there, and 2 there. So again, the elimination is going to come from the carbon with the most hydrogens. And so that means the double bond has to be right there. So that's going to get us D. Another way to look at it, if we classify the alkene products, we want the least substituted one. So one last reaction. Again, this is a 2-step thing. We first activate the nitrogen and then we do an elimination. So here we're starting with a tertiary amine. So it still has a lone pair. That lone pair is nucleophilic. We're going to treat it with that reagent MCPBA. So it has that electrophilic oxygen. So the nitrogen's going to attack that. And then we end up with this thing, which is called an N-oxide. So those are stable intermediates. Typically, those things will just form, any sort of molecule that has a nitrogen in it will readily form N-oxides in the presence of air. The rate at which it does it depends on sort of the ambient conditions. But this oxygen can now act as a base and do an elimination within the molecule itself. So we might run a second or two over here. So what we have to consider is we need to form an alkene. So we look at the carbon bearing the nitrogen, and then we have to go one more carbon out. That's what we're considering in terms of the hydrogen that's going to be abstracted. So this molecule has 2 beta carbons and a total of 5 beta hydrogens. And it's kind of the opposite now, where you want to form the more substituted alkene. And so when you look at those beta carbons, you want to abstract from the one that has the least number of hydrogens. So this one has 2, that one has 3. And so we can kind of wrap this up real quick. An elimination will happen from those 2. And I'm just going to focus on those 2 carbons and just put an alkene there. So we have 1, 2, 3, 4, 5 carbons. And then we do an elimination within the molecule to install that alkene. So that gives the more substituted alkene at this point. So we went a smidge over